Welcome back, everyone, for another deep dive. This time, we're going to be tackling a topic that's, it's going to stretch your brain in the best way possible, I think.
Oh, yeah.
We got a fascinating article sent in by one of our listeners from scitechdaily.com about an experiment linking quantum mechanics and information theory.
Wow.
Yeah, and it's a wild ride, I gotta say. Get ready to explore the bizarre world of wave-particle duality.
Here we go.
That mind-bending concept where something can be both a wave and a particle at the same time.
You're right.
We're going to unpack what this new research reveals.
Okay.
First, I think it would be good to set the stage with a little bit of history.
Yeah, for sure. I mean, it's amazing to see how our understanding of light has evolved over the centuries.
Yeah.
You know, we're talking about a fundamental question that has puzzled scientists for ages.
And it all started way back in the 17th century with Isaac Newton, who proposed that light was made up of tiny particles. It's a pretty intuitive idea when you think about how light seems to travel in straight lines, bouncing off objects.
Yeah, that particle theory worked well for a while.
Mm-hmm.
It explained things like reflection and refraction. But then in the 19th century, scientists started observing phenomena that just couldn't be explained by particles alone.
So it seems like Newton was only half right.
Yeah.
What happened next? Did someone finally figure out that light was a wave?
Exactly. Scientists like Thomas Young and Augustin Jean Fresnel conducted experiments showing that light could diffract and interfere, just like waves in water.
I'm thinking about the double slit experiment.
Exactly.
That was pretty cool.
Of a game changer, definitely proving that light could behave like a wave.
So for a while, the wave theory reigned supreme.
Yeah.
But science is all about challenging assumptions.
Always.
And the early 20th century brought a whole new wave of discoveries, literally and figuratively.
Right. It was a time of radical shifts in thinking. Along came Max Planck and Albert Einstein, who showed that light energy wasn't continuous, but came in these discrete packets called quanta.
Yeah.
This laid the foundation for quantum mechanics.
Oh.
Einstein even explained the photoelectric effect, where light shining on a metal surface knocks electrons loose by suggesting that light acts like a particle.
A photon.
A photon in this case.
So we had these two seemingly contradictory ideas.
Yeah.
Light as a wave, and light as a particle.
Right.
It's enough to make anyone's head spin.
Oh, for sure.
How did scientists even begin to reconcile those two seemingly opposite concepts?
Well, that's where Niels Bohr's brilliance comes in.
Okay.
He introduced what's called the complementarity principle,
Oh, right.
which essentially says that light isn't flip-flopping between being a wave or a particle. It's both all the time.
Okay.
But we can only observe one aspect at a time.
No.
It depends on how we choose to measure it.
It's almost as if the universe is playing a cosmic game of hide-and-seek with us.
Oh, that's good.
The more we try to pin down one aspect of light, the more the other aspect slips away.
That's a great analogy.
I like that one.
And this leads us to a crucial concept, Heisenberg's uncertainty principle,
Yeah.
which states that we can never know both the position and momentum of a particle with perfect accuracy.
So it's like there's this fundamental limit to what we can know about the quantum world.
Yeah.
But where does information theory come into all of this?
That's where a groundbreaking 2014 theoretical paper from a team in Singapore comes into play. They took the complementarity principle and mathematically linked it to something called entropic uncertainty.
Okay, I'm intrigued.
Yeah?
What exactly is entropic uncertainty? Does it have something to do with black holes?
Not quite, although black holes are definitely fascinating.
Oh, okay.
In simple terms, entropic uncertainty is a measure of how much information is missing about a quantum system. Like there's always a hidden piece of the puzzle, no matter how clever we are with our measurements.
I see.
Think of it this way.
Okay.
Even in the quantum world, there are gossip girls and guys. No matter how hard we try, we can't get all the juicy details.
Right.
There's always going to be some missing information.
So this research shows that there is a fundamental limit to what we can know about the quantum world.
Right.
And the Singapore team found a way to connect that limitation to the way we measure light.
Exactly.
They found that regardless of how you choose to measure a quantum system, whether you're looking for its wave-like or particle-like properties, there will always be at least one bit of information that remains unknown.
Exactly.
This missing bit represents the aspect you didn't measure.
Yeah.
So what this means is that even though light embodies both wave and particle aspects simultaneously, we, as observers, are stuck with a limited perspective based on how we choose to measure it.
Precisely. Now hold on tight.
Okay.
Because this is where things get even more interesting.
Right.
The article you sent us describes an experiment at Linköping University in Sweden that actually put this theoretical prediction to the test.
So they knew the theory,
Right.
but could they actually prove it? That's where the Linköping experiment comes in. Okay, let's step into that lab in Sweden and see how they tackled this challenge. What did they actually do in this experiment?
They started with a beam of photons, but not just any photons.
Okay.
They used photons with something called orbital angular momentum. Think of it this way. These photons have a twist, like a corkscrew.
Oh, wow.
This special kind of light allows them to encode more information.
So they're using light that's a little more complex than your average light beam. Why is that important?
Well, that extra complexity gives them more to work with.
Okay.
When it comes to measuring the different aspects of the photons, now they shine this twisted beam of light into an interferometer, which is essentially a device that splits the beam in two using a beam splitter.
Yeah.
Each half of the beam travels along a different path.
I'm picturing a beam of light splitting in two, each half taking a different route and then meeting up again. Classic interferometer setup, right?
Exactly.
Yeah.
But here's where things get really clever. They have a second beam splitter placed right where those two paths intersect. And this second beam splitter is the real star of the show.
Why is that second beam splitter so special? What does it do?
Think of it like a dial. They can adjust this second beam splitter to control how much of the wave-like or particle-like behavior they want to measure. They can essentially tune their observation.
Wait a minute. Are you saying they can actually choose how to observe the quantum world?
Yeah.
They can make the photons look more like waves or more like particles just by adjusting this beam splitter?
That's exactly what they did. It's the key to the whole experiment.
Yeah.
This ability to fine-tune their measurement allowed them to test that 2014 theory about entropic uncertainty.
Okay, my mind is officially blown.
Yeah.
So they have this beam of twisted light, they split it in two, the halves travel different paths, they meet up again, and then they have this quantum dial that lets them choose how they want to measure the photons. What happens when they start tweaking this dial? What did they observe?
Remember that concept of entropic uncertainty we talked about earlier? That minimum amount of unknown information that always exists? Well, their results confirmed that no matter how they adjusted that second beam splitter, that minimum uncertainty was always present.
So even though they could control what aspect of the photon they were measuring, there was always this hidden piece of the puzzle that remained elusive.
That's a great way to put it. They could choose to see more of the wave nature or more of the particle nature.
Okay.
But they could never see both perfectly clearly at the same time. It was always at least one bit of information that remained hidden.
Wow.
Just like the theory predicted.
This is incredible. It really drives home the point that there are fundamental limits to what we can know about the quantum world.
Yeah.
We're peeking into a realm where our everyday intuition just doesn't apply.
It's true.
But you mentioned earlier that this research could have some practical implications, right?
Absolutely.
So it's not all just theoretical mind games?
Absolutely not. This is fundamental research, but it has the potential to revolutionize a number of fields.
Like what?
The article mentioned quantum communication, metrology, and cryptography as areas that could benefit from this research.
Okay, color me intrigued. Let's break those down one by one. What could this mean for quantum communication?
Imagine a world where communication is completely unhackable, where you could send information with absolute certainty that no one could intercept it. That's the dream of quantum communication. And this research, by probing the limits of quantum measurement, could help us get there.
So this seemingly esoteric research could have real-world applications for building ultra-secure communication networks. That's pretty amazing. What about metrology? How could this research impact our ability to make precise measurements?
Well, metrology is all about measurement.
Yeah.
And in the quantum world, precise measurement is everything.
Right.
Think about it. If we can understand and exploit the fundamental limits of measurement in quantum systems, we could potentially develop new technologies to measure things like time.
Gravity and magnetic fields with unprecedented accuracy.
That's mind-boggling. It could revolutionize scientific research, improve navigation systems, and even lead to breakthroughs in medical diagnostics. What about cryptography? How does this research relate to keeping our information secure?
Cryptography is all about creating codes that are difficult to crack. And quantum mechanics, with its inherent uncertainties and complexities, offers a whole new toolbox for creating ultra-secure encryption methods. This research, by deepening our understanding of those uncertainties, could pave the way for virtually unbreakable codes.
So this experiment while exploring the very foundations of quantum mechanics, could lead to practical applications that impact how we communicate, measure the world around us, and keep our information secure.
And it gets even wilder. These researchers aren't stopping there.
Oh, really?
They're already planning their next experiment, and it's a doozy.
Oh, I love a good cliffhanger. Tell me more. What's the next step in this quantum adventure? They want to change the setting of that second beam splitter, that quantum dial we talked about.
Yeah.
Right before the photon arrives. Imagine the photon is racing towards the splitter, and at the last moment, they switch the setting.
Wow. So they're going to try and trick the photon to see if they can force it to reveal its true nature.
Exactly. And the implications of this experiment are huge. It could shake up our understanding of causality and even time itself.
Okay, my mind is officially in overdrive. We're diving even deeper into the quantum rabbit hole in our final segment. I'm still trying to wrap my head around this. They're going to change the measurement setting while the photon is in flight. It's almost like asking the photon to decide its nature mid-journey, wave, or particle.
That's a great way to think about it.
Yeah.
And the implications of this experiment are profound. What if the photon somehow knows in advance how it will be measured? That would challenge some of our most fundamental assumptions about cause and effect. Maybe even about time itself.
That's stepping into some serious science fiction territory. But I remember the researchers mention potential applications in secure communication. How could this experiment impact that?
Well, one of the biggest challenges in secure communication is ensuring that the encryption keys, the secret codes used to scramble and unscramble messages, are kept secret.
Right. Secure key distribution is absolutely crucial.
And this is where the mind-bending nature of quantum mechanics could come in handy. Imagine encoding the key information onto a photon and sending it to the recipient. Now, because of these inherent uncertainties we've been talking about, if anyone tries to intercept and measure the photon, they inevitably change its state. They can't peek without leaving a trace.
So it's like a tamper-proof seal for the key. Any attempt to eavesdrop would immediately be revealed.
Exactly. This kind of quantum key distribution could revolutionize cybersecurity. And this experiment, by probing the very limits of measurement and causality in the quantum world, could help us get there.
It's amazing to think that we started with a simple question, is light a wave or a particle? And ended up on this incredible journey through the mind-boggling world of quantum mechanics and information theory.
I know, right?
We explored historical breakthroughs, delved into the counterintuitive concepts of wave-particle duality and uncertainty, and even glimpsed potential future applications that could reshape communication and security as we know it.
Absolutely. It's a testament to the power of scientific curiosity. And this new research is really just the tip of the iceberg. Who knows what other mysteries are waiting to be uncovered? What other connections between quantum mechanics and information theory remain to be explored?
That's a great point. And it leaves us with a question for all of you listening. If the act of observation can influence the behavior of photons, what does that say about our role in shaping the world around us? It's a big question, and one that physicists and philosophers will likely be grappling with for generations to come. Thank you for joining us on this deep dive into the fascinating world of wave-particle duality. We encourage you to share your thoughts and questions, and until next time, keep exploring the universe with a sense of wonder.